Here we go. Section 3.2, understanding relations and functions. I can't tell you guys enough how fundamental this section is and for basically the entirety of algebra. What you learn here is, pertains to everything pretty much in algebra. So it's very important we understand these fundamental things. Okay, so let's starting off, understanding relations. A relation is a set of ordered pairs x, y, where x is the input value, y is the output value. The domain is all possible inputs of a relation. The range is all possible outputs of a relation. For example, the given relation represents the number of whole wheat cracker boxes sold and the money earned. So, for instance, we're saying one cracker box was sold, $4 was earned. 2 cracker boxes was sold, $8 was earned. 3 boxes are sold, $12 are earned, and 4 boxes are sold and $16 is earned. Now, domain is all the input values, all the x values. In this case, it's the number of boxes sold. So 1, 2, 3, and 4. This 1, 2, 3, and 4. Those are all the x values. Those are all the input values of the boxes that were sold. The output value is the result of selling those boxes. So they have a little typo here. It's supposed to be $4, $8, $12, and $16. Those are all the outputs. That's the range. Those are the y values. That is the result of what happened with the number of boxes that were sold. So for the following relation, put the input x is the ages of boys and the output y is their corresponding height in inches. So x values here represent the age and the y values represent the height. So for a 7-year-old, he was 41 inches tall. For an 8-year-old, he was 45 inches tall. And I'm reading these numbers right here. 9-year-old was 49 inches tall. 10-year-old was 52 inches tall. Another 10-year-old was 53 inches tall. 11-year-old was 55 inches tall. And 12-year-old was 59 inches tall. The x values here are all the domains, all the input values, which was age of the boy. The y value is the range. Based on the age, how tall were they? So the y value is the height, who's our range. Plot the points on the graph. Okay, so we have 7, 41. 7 and 41 is about there. 8 and 45. 8, 45 right here. 9 and 49 right there. 10, 52. And we have 1053 as well, so we're going to have 2 points right there. 1155 and 1259. There they are. I'm not going to connect the dots here. I'm not connecting the dots because there's no reason these points have to be connected. I'm just plotting the 7 different age boys and their heights. That's it. So I should have 7 dots on my graph. I do, and now I'm good. If you can't tell they're 7, it's because these 2 dots are really close together. It's hard to tell. All right. So complete the mapping diagram. So a mapping diagram is just how we connect the input values with the output values, or in a sense, the x values with their y values. So based on the ordered pairs that we saw earlier, 7 maps to 41. So we're going to draw a line that draws 7 to 41. 8 maps to 45. So we're going to draw a line from 8 to 45. 9, if we go back again, 9 maps to 49. And you can look at this table if you need. I'm not going to continue scrolling, but you can look at the table in your own book. 9 to 49. 10 goes to 52 and 53. 11 goes to 55, and 12 goes to 59. State the domain of the relation. So the domain, again, was all the input, all the x values, which were the ages, 7, 8, 9, 10, 11, and 12. Now, it's very important that you point out, notice Even though we had 2 boys that were at the age of 10, I didn't include them twice. If once I include 10, I've included 10 and I don't have to repeat it. 10 is already included, okay? So you can see that's why they didn't double it up here. 10 is included in the range, in the domain, but then of course you can see that it mapped to the 2 values in that range. The range, however, again, all the values. So we have 41, 45, 49, 52, 53, 59, and 55. All right. The number 10 appears twice in the X column of the table. How many times is it written in the domain? Once. Because once it is included, we do not need to duplicate it. We're saying we already have a boy that's 10 years old. We've included it. We've noted it. There's that value. What does the book say? The book says the number 10 is written only once in the domain. The domain is a list of the input values, and a number should only be listed once, no matter how many times it actually appears in the relation. So yeah, only appears once, only has to show up, or it doesn't matter how many times it appears, we only have to write it down once to say, hey, we've accounted for it. Okay. We don't have to account for it every single time. Recognizing functions. A function is a type of relation in which there are there is only one output value for each input value. So it's this is definition. I can't believe I messed it up. Say it again because it's very, very important. I'll put a star next to it and how important it is. A function is a type of relation in which there is only one output for each input. Okay. Now, to kind of illustrate what that looks like, if you look back at the previous example here, this last example would not be a function. Here's the reason why. There's only one output for each input. The number 10 here, that input has more than one output. It's only supposed to have one output for each input. So that input has more than one output. So that's the reason why that last problem would not have been considered a function. All right, for each input value, there's a unique output. Y equals x squared. When x equals 3, y will always be equal to 9. So yes, basically, when you plug a number in, you're not going to get 2 different answers out. When you plug a number in, you only get 1 answer out. That's the idea of how a function works. It's not going to be a function if you plug in a number and you get 2 different answers. Give the domain and range for each relation. State the corresponding outputs for the given inputs in context and explain whether the relation is a function. The given relation represents the number of students and the number of classrooms the school has to have for the corresponding number of students. So there's 40 students, and they need 2 classrooms. If there's 45 students, they need 3 classrooms. If there's 50 students, they need 4 classrooms. And those points are plotted here. 40 students, 2 classrooms. 45 students, 3 classrooms. 50 students, 4 classrooms. Domain is those input values, those x values of 40, 45, and 50. The range is the y values 2, 3, and 4. Now, since they're one-to-one mapped, 40 goes to only 2, 45 goes to only 3, and 50 goes to only 4, because each of these only has one line coming off of it, it is considered a function. So yes, it is a function. The given relation represents the amount of gas in gallons and the distance traveled in miles from that amount of gas. So if you use 10 gallons, go 150 miles. 16 gallons will go 240 miles. 17 gallons will go 240 miles. And 20 gallons will go 300 miles. So this was measured based on someone's gas tank, I suppose. Okay, so the domain are all the x values. Again, the input values, which are the gas usage. So we have 10 gallons, 16, 17, and 20 referred to in this problem. The domain represents gallons. The range is the distance that we're able to drive. So we have a duplicate, so we don't have to repeat it twice. It's 150, 240, and 300. The range represents the distance driven. Oop. Now, for an input of 10, there's an output of 150. For an input of 16, there's an output of 240. For an input of 17, there's an output of 240. And for an input of 20, there's an output of 300. The relation is a function. Each domain value is paired with exactly one range value. Now, you might be wondering, what do you mean? If you look at it, there's two lines that go to 240. That is okay. That is okay. What we cannot have is two lines coming from an x value. We can't have two lines come from 10 or two lines come from 16 or two from 17. We can't have anything like that. We have to have one line coming off each of these. It doesn't really matter what happens on the y side of things, what happens in the range side of things. In fact, we could have all of these just go to 240. It would still be a function. Okay? So yes, you can have duplicate y values. You just can't have duplicate x values and multiple lines coming off of x values. Think of it like this. I've always explained it this way. Think of x as in people and y as in places. Now, for people, we can't have the same person in two different places at the same time, right? A person cannot be in two places at the same time. I can't have someone go to Billy's house and Fred's house at the same time. They can't physically be in those two places at the same time. Okay, unless it's the same. Don't get ridiculous. Don't start trying to be funny here. Okay, one person can't be at the grocery store, right, and at the movies at the same time. They can't be in two places at once. That's why it wouldn't be a function if you ever had that. However, you can have multiple people go to the same place. So, for example, 16 and 17, those people can hang out at 240's house, right? You can have two people in the same house, but you can't have one person in two houses. Does that make sense? That's kind of the distinction between what makes a function or not. So yeah, it can be a little confusing, but I think that helps make it a little more understandable. If each month in a year was paired with all the possible number of days in the month, will the result be a function? This is actually kind of interesting. If each month in a year was paired with all the possible number of days in the month, will the result be a function? I think the answer is no. What does the book say? I'm kind of curious what the book says. Okay, well, the book writes, okay, there's two ways you can argue this. The book says yes, it would be a function because you would basically have January would map with 31, February would map with 28, March would map with 31, April would map with 30, right? So there'd basically be every month would have a corresponding y value, and there's no duplicating months. You're not going to have two Januaries, 2 Februaries, 2 Marches, etc. So the book says yes because of that reason. But I say no, actually, because February could be 28 or 29, right? So I get it says in a year, each month in a year. So if you're only talking about 1 year, then yes, February can't both be 28 days and 29 days in the same year. 1 year it's going to be 28 days, another year it'll be 29. So if you're talking about in the same year, then yes, it's a function. But if you talk about in general, then no, it wouldn't be a function because February could have 28 and 29 days. February, think of it, could map to 28 and to 29. So remember, you're not supposed to have two stems coming off of your domain. So I would argue no for that reason. But if you're talking about just specifically 1 calendar year, if I'm just talking about specifically 2019 and that was it, then yes, it's a function because February has 28 days and you're not repeating months at all here anywhere. So that's a very interesting question because you can kind of argue that 2 different ways. Number 3, okay, the relation represents the number of books sold and the price for the corresponding number of books. So 2 books cost $4, 3 books cost $6, 4 books cost $7, 5 books cost $9. And that graph is shown here. You have the mapping diagram. 2 books sold is $4, 3 books sold is $6, and so on. You can see how those are mapped together. So give the domain and range of each relation and interpret them in context. So domain here is just 2, 3, 4, and 5. It represents books sold. Range is 4, 6, 7, and 9, and it represents money. I guess price of books. Was there anything else? State whether given inputs, context, explain whether the relation is a function. So this one is yes, a function. And my reasoning behind it is because each book sold maps to only one price range. So it would not be a function if, for example, 2 books cost $4 and $6, because then you're kind of changing the price, right? You're saying that, hey, here's 2 books, but for one person, it's going to cost $4, and for another person, it's going to cost $6. That wouldn't be a function because then you're saying 2 books cost different amounts of money. That would make it not a function, but we don't have that here, right? 2 books sold is $4 strictly, and so on. Each of these is paired to exactly one or the other. So yes, it's a function. Number 4, the relation represents the time spent exercising and the number of calories burned during that time. All right, so 20 minutes exercising, 50 calories burned. 35 minutes exercising, 85 calories burned. 35 minutes, 85 calories burned. 60 minutes, 100 calories burned. There's your graph. Okay, so domain is going to be 20, 30, 35, and 60. This is the minutes of working out. The range is going to be 50, 85, and 100, which is the calories burned. And this is a function as well. Yes, it's a function. And again, the reason is, if you look at your mapping diagram, it's a dead giveaway. Each x value has one corresponding link off of it. Okay, you don't have to focus on where it ends up in the y values. You can have multiple x values go to the same y value. You just can't have it the other way around. You can't have x values go to different y values. That would be bad. You can see that each x value has one branch stemming off of it. That's how I can tell it's a function. All right, use the vertical line test to determine if each relation is a function. So vertical line test basically means that for each vertical line you draw, you're only going through 1 point and 1 point only. It would fail the vertical line test if you draw a vertical line and you go through more than 1 point. So draw a vertical line through each point of the graph. So you can see they've done that here. So for the first line, they go through 1 point, which is good. The second line goes through 1 point, which is good. And this goes on except for the fourth line. The fourth line, actually, as you can kind of see, it's very tough. But that's going through 2 different points. That line goes through 2 different points. Kind of zooming in on it there. And that's not allowed. If it passed the vertical line test, it can only go through 1 point at most. So it cannot go through more than 1 point. So therefore, it's not a function. So we're going to do it for this one. Draw a vertical line through each point of the graph. Okay, what am I supposed to be? What's supposed to be on my graph? Is it supposed to be something on my graph? Oh, I guess the distance in gallons one again. So we're going to have to go back up here. They're talking about this graph. So 10, 150. We got to make it ourselves. Okay, 10, 150. It was 16, 240. I believe it was 17, 240, right? 16, 240, 17, 240, and 2300. 16, 17 were both at 240, which is like right there and right there. And then 20 was at 300. So a vertical line test only goes through that point there, only goes through that point there, only goes through that point there, only goes through that point there. Basically, if any points are stacked, that's bad news, right? If I had a point above another point stacked, that's bad news. But if they're next to each other like this, it's fine because they're not stacked, right? It's only if you stack them that they'd pass or that they would fail the vertical line test. So the answer is no. So it's a vertical line. How do they write here? I want to know what they fill in their blank with. Does not, since a vertical line does not pass through more than one point, the graph passes the vertical line test, so the relation is a function. So the vertical line test, why does it work? Well, it works because you're checking for each x value, right? So drawing a vertical line at 5, for example, right? You're checking that x value. Drawing a vertical line at 10, you're checking that x value. If it has more than one point, then you're saying that that x value has two different y values. So for example, 10 in this case would map to 150 and it would map to 225 if it were the case, if it had those 2 points on it. You're saying that 10 goes to two different places. So that's why it works the way that it does. Draw a vertical line test to determine whether it's a function. So the vertical line test here, no matter where you draw a vertical line, draw anywhere, you're only ever going to hit one part of the graph, of one part of the function. So for number 6, it does pass. But for number 7, you can see when I draw a vertical line, I'm going through 2 points in all of these vertical lines, except the only time I wouldn't go through 2 points would be right there. I'd only go through 1 point. But because I can draw a vertical line that goes through more than 1 point, for example here, right? It's not perfectly straight, but you get the idea. Imagine it was perfectly straight, right? Because it goes through more than 1 point, it fails. So that one does not. It is not a function. All right, I'm going to stop it here, guys. I will see you later on.